Hello everyone, welcome to my final project proposal, high-resolution object-based analysis of land cover change around Central Michigan University using multi-temporal NAIP imagery and LiDAR data. My name is Tristan Mathis. This project proposes to analyze land cover changes around Central Michigan University using high-resolution imagery and LiDAR data. The study will focus on understanding how urban development, agriculture, and forested areas have changed over time. By integrating spectral and elevation data with object-based image analysis, this project aims to highlight the potential for geospatial technologies to provide actionable insights for environmental monitoring, urban planning, and land use management. My project motivation is that understanding land cover change is vital for planning and resource management. Central Michigan University's surrounding area is a mix of forests, farmland, and urban areas, each with important environmental, economic, and social implications. Urban expansion, forest fragmentation, and changes in agricultural patterns all impact the local ecosystem and community planning efforts. High-resolution imagery allows us to capture subtle changes such as small-scale urban development or agricultural expansion that coarser or lower resolution imagery datasets might miss. Overall, this information can guide sustainable development and conservation strategies with the idea to provide tangible value to city planners and local authorities. As you can see in both of the color infrared images, you can clearly see a preliminary difference in just a 6-year time span of a changing landscape between buildings being built, waterscape changes expanding or shrinking, or agriculture versus grass dense areas. The primary objective of this project is to quantify the extent and changes in agriculture, forested, and urban areas around CMU. Specifically, I am aiming to first determine how much land each class occupies. Second, detect transitions such as agricultural land becoming urbanized or forests becoming cleared. And third, apply object-based image analysis metrics, spectral, geometric, and contextual to improve classification accuracies. With the inclusion of the LiDAR data, this will allow me to include height information, which is particularly useful for distinguishing wooded areas versus ground level vegetation. Ultimately, this project highlights how high-resolution data multi-temporal analysis can uncover the fine scale of landscape dynamics. The study area encompassed Central Michigan University and surrounding areas in Mount Pleasant, Michigan. This study area included a mix of agricultural fields, wooded areas, and urban infrastructure, making it an ideal location for demonstrating object-based image analysis. The 1.24 square miles, previously reduced from 22 square miles, covers sufficient diversity in land cover to observe meaningful change over time, while remaining manageable for processing high-resolution imagery and LiDAR data. The primary data source is NAIP imagery, offering 0.6 meter resolution across 4 spectral bands, those being red, green, blue, and near-infrared. Imagery from 2016 and 2022 allowed for a change detection over a 6-year period. Overall, the data was obtained from USGS Earth Explorer. The imagery files were clipped to the area of interest to create a continuous raster for analysis. The NAIP imagery overall provides detailed spectral information that is ideal for differentiating between vegetation, urban surfaces, and other land cover types. The other data set that I used was LiDAR-derived elevation data from the USGS 3DEP program, providing high-resolution terrain information with roughly 1 meter point spacing. Although the data set is from 2017, it doesn't necessarily match the NAIP imagery exactly. I aim to use it to serve as a reference for distinguishing trees from lower vegetation and/or urban surfaces. Including elevation data in the classification process helps improve accuracy by adding a geometric dimension to spectral information, which is especially useful in high-resolution object-based image analysis. For this project, I used 2 main software packages, that being eCognition and ArcGIS Pro. Before classifying the imagery in eCognition and ArcGIS Pro, I pre-processed the data to make sure everything aligned correctly and was in the same coordinate system. There were multiple NAIP tiles that were mosaicked and clipped to the study area to create a continuous raster for each following step. I also imported LiDAR point cloud data to generate a DEM and a DSM to create an NDSM as a reference layer to help separate tall vegetation and buildings from ground level features. Next, I segmented the imagery in eCognition using multi-resolution segmentation to capture both small and large features, while the quad tree method was used to help manage hierarchical structures. This was useful for processing large areas while keeping detail for smaller features like roads, fields, or tree clusters. I also used spectral difference segmentation to separate objects that are connected but had different spectral properties, like adjacent crops or rooftops with different colors. Using these different segmentation parameters and combining these methods overall provided a strong foundation for object-based classification of agriculture, forest, urban areas, and water, and other land cover classifications. After segmentation, I created an interpretation key to make sure feature extraction was accurate. The NDVI indice was used to separate vegetated from non-vegetated areas. Elevation data helped identify tree heights and building heights, helping distinguish wooded areas from agricultural fields and buildings from ground level features. Shape and texture metrics were also used to help separate urban surfaces from irregular agricultural plots, improving overall classification accuracy. I then began to classify each object to a land cover class using supervised object-based methods using multiple metrics, that being spectral, geometric, and textural, which made it easier to separate similar land cover types. This approach worked especially well with high-resolution imagery where pixel-based methods are often too detailed. Finally, I overlaid the two classifications to detect changes over time. This highlighted any urban expansion, deforestation, or changes in agricultural use. And then, as well as quantifying these transitions, helped provide insights into land use dynamics and could help inform campus planning or conservation efforts in the future. Integrating the spectral imagery with elevation data also improved accuracy and classification to ensure that the results were reliable. Overall, that this workflow provides a clear, repeatable method for analyzing high-resolution land cover change over time. As mentioned previously, as part of the pre-processing workflow, LiDAR point cloud data was downloaded from the USGS 3-depth national map and imported in ArcGIS Pro. From the point cloud data, a digital surface model was generated using first return LiDAR points representing the top surface of features such as vegetation and buildings. A digital elevation model was then created as well using ground classified LiDAR returns to represent the bare earth terrain. Using the raster calculator analysis tool in ArcGIS Pro, the DEM was subtracted from the DSM to produce a normalized digital surface model, or NDSM, which represents object height above ground. This NDSM was then imported into eCognition and used as a conditional parameter during segmentation classification to help distinguish tall features such as trees and buildings from ground level surfaces. These were the rule sets that I developed in eCognition for segmentation and classification based on the interpretation key tables that I generated, which involved gathering different spectral, geometric, and textural properties from the 8 land cover classification types that you'll see later on. So notable conditional parameters that I used was NDVI values, NDSM, mean near infrared value, number of aerial pixels, and length and width properties. There was also some manual reclassification and refinement after these conditions were ran to correct for any errors in the classification. For my results from 2016, this map displays the land cover classification of 8 land cover types generated from the previous rule sets in eCognition. I produced a summary statistics table to summarize the land cover distribution for the study area based on the classification results. Grass is obviously the dominant land cover type here, as you see on the map and in the table, covering approximately 937,000 square meters, which represented about 34.4% of the total study area. Pavement was the second largest class, encompassing 22.8% of the landscape, while trees made up about 17.3% of the area, covering approximately 472,000 square meters. Buildings represented about 11.8% of the study area, while roads accounted for about 5.6%. Agricultural land covered about 4.9% of the landscape. Smaller classes included the bare earth and water, both representing about 1.7 or 1.5% of the total area. Overall, the results indicated that the study area is primarily composed of grass and paved surfaces with significant tree cover and developed infrastructure, while agricultural land, bare earth, and water represented smaller portions of the landscape, at least collected for 2016. I used 2 sampling approaches for the confusion matrix accuracy assessment for both 2016 and 2022 to provide a more complete review of the classification results. Stratified random sampling was used to calculate overall accuracy in the kappa coefficient because it reflected the true distribution of land cover classes across the study area. For example, in this approach, the larger classes received more assessment points, which allowed for a more accurate overall accuracy to represent how well the classification performed over the study area as a whole. It then also used equalized stratified sampling to evaluate individual land cover classes by assigning an equal number of assessment points to each class. This ensured that the smaller classes, such as water or bare earth, were equally represented to allow for a reliable calculation of producers' and users' accuracy. Without using equalized sampling, these smaller classes might have received very few validation points, making class-level accuracy metrics unreliable. By using both approaches, the assessment provided a landscape-level evaluation of overall map accuracy and detailed understanding of how well each individual land cover class was classified. The confusion matrix accuracy assessment for the 2016 classification showed strong overall performance. Using stratified random sampling, the weighted overall accuracy was 92%, with a weighted kappa coefficient of 89.9, showing a very high level of agreement between the classified map and the ground or reference data. To evaluate individual land cover classes, equalized stratified sampling was used with 50 validation points per class to calculate producers' and users' accuracy. Agriculture performed extremely well, with a producer's accuracy of 100% and a user's accuracy of 98%. Bare earth achieved a producer's accuracy of 95% and a user's accuracy of 88%, while buildings were classified very reliably, with both producers' and users' accuracies at 98%. The grass, however, had a lower producer's accuracy of 73%, but a high user's accuracy of 92%, suggesting that some real grass areas were misclassified as potentially other vegetation types, but areas labeled as grass on the map were generally correct overall. Pavement showed strong performance with an 85% producer's accuracy and a 98% user's accuracy. Roads as well achieved a producer's accuracy of 100% and a user's accuracy of 94%, indicating that road features were consistently identified as well. Trees tend to show the opposite pattern in relation to grass, with a high producer's accuracy of 94%, but a lower user's accuracy of 74%, suggesting that while most real trees were captured, some areas labeled as trees may have actually represented other vegetation types as well. Finally, the water achieved perfect producer's accuracy and user's accuracy of 98%, demonstrating very reliable detection of overall water features. Overall, these results indicated that the classification performed very well across most land cover types, with the primary confusion occurring between spectrally similar vegetation classes such as grass and trees. My results for the land cover and percent coverage for 2022, I generated a summary statistics table showing the 8 land cover classes distribution for the study area in 2022. Similar to the early year, grass remains the dominant land cover class, covering approximately 962,000 square meters, which represented about 34.3% of the total study area. Pavement was the second largest class and increased substantially, covering about 773,000 square meters, or about 27.6% of the landscape. Trees accounted for approximately 14.5% of the study area, while buildings represented about 11.9%. Roads also covered approximately 5.7% of the landscape. Smaller classes included agriculture and water, as well as bare earth, all well under 3%. Overall, the results suggested that the study area continued to be dominated overall by grass and developed surfaces, with pavement increasing compared to the early year, while tree cover and agricultural areas have slightly decreased. The confusion matrix accuracy assessment for the 2022 results showed a very strong overall classification performance. Using stratified random sampling, the classification achieved an overall accuracy of 93% with a kappa coefficient of 91%, indicating strong agreement between the classified map and the ground or reference data beyond chance. To evaluate the individual land cover classes, used equalized stratified sampling with 50 validation points per class to calculate producers and users' accuracy. Agriculture performed extremely well with a producer's accuracy of 100% and a user's accuracy of 98%. Bare earth also performed well with a producer's accuracy of 95% and a user's accuracy of 86%. Buildings were also classified very accurately with a producer's accuracy of 97% and a user's accuracy of 96%. Grass achieved a producer's accuracy of 87% and a user's accuracy of 94%, indicating that most grass areas were correctly identified and that pixels labeled as grass on the map were generally reliable. Pavement had a producer's accuracy of 85% and a very high user's accuracy of 98%, suggesting that while some areas were missed, areas classified as pavement were generally pretty accurate. Roads also showed very strong results with both producers and a user's accuracy of 98%. The trees class had a producer's accuracy of 93% and a user's of 86%, indicating strong detection of tree cover with some minor confusion with other vegetation types. Finally, water achieved perfect accuracy with both producers and users' accuracy of 100%, demonstrating extremely reliable classification of the water features for the 2022 land cover data set. Overall, the results show that the classification performed very well across all land cover classes, with the highest accuracy occurring clearly defined features such as water, buildings, and roads, while minor confusion occurred among vegetation classes. This slide displays a side-by-side comparison of the land cover classification changes between the 6-year time frame. I highlighted a few areas that were more obvious from a classification perspective, showing typically where the changes most often occurred. As you can see on the left, which represents the top half of the study area, and on the right represents the bottom half of the study area. In the classification pictures on the left, you can clearly see differences in buildings and other construction infrastructure being created between the 6-year period. On the right, you can see increase in pavement areas or parking lots and reduction in agricultural areas, potentially due to seasonal changes or harvesting of crops. You can also see some combination of decreases and increases of certain water areas over the 6-year period as well. The results of this project directly address the original objective of mapping and analyzing land cover changes between 2016 and 2022 using object-based image analysis with NAIP imagery and LiDAR-derived elevation data. The classification successfully identified major land cover classes, including agriculture, grass, trees, pavements, roads, buildings, bare earth, and water. By comparing the classified maps between the 2 years, I was able to quantify changes in land cover distribution and evaluate how the landscape evolved over the 6-year period. The accuracy assessments supported the reliability of the classification with high overall accuracy and strong agreement values, indicating that the workflow effectively captured the dominant land cover patterns within the study area over the course of the 6-year period. Several components of the workflow worked particularly well, integrating LiDAR-derived height information through the normalized digital surface model significantly improved the ability to distinguish between tall vegetation, buildings, as well as certain ground-level features in classes like grass or pavements. Object-based segmentation also allowed spatial and textural characteristics to be incorporated, which improved classification compared to pixel-based approaches. However, there were some challenges that I encountered during the process. Certain land cover types with similar spectral signatures, such as grass in agricultural fields or pavement in bare earth, were difficult to separate consistently. Segmentation parameters also required multiple adjustments to avoid over-segmentation or merging of distinct objects. These challenges were addressed often by refining these segmentation scale parameters and weighting, incorporating additional object attributes such as height and shape metrics, and iteratively testing those classification condition parameters and rules. If I were to start this project again, I would spend more time optimizing the segmentation parameters early in the workflow, and I would also consider incorporating spectral indices as well, other ones. The most significant thing I learned from this project is how critical segmentation quality and feature selection are in object-based image analysis. Even small adjustments to segmentation parameters or feature thresholds can have a large impact on classification accuracy, highlighting the importance of iterative testing and careful parameter selection when working with high-resolution remote sensing data. I appreciate everybody for listening to my project on object-based image analysis using high-resolution imagery data. Thank you.